Hi, this is Wojtek Powiertowski from Facebook. I'm a Silicon Security Architect, and I'm here today to talk about some recovery concepts that we are working through in the OCP security workgroup. I wish we could do this in person, but no, let's do this online instead. So, kind of wanted to start with where are we now as an industry right now, and the what we see most as kind of the biggest pain point is that we still leverage a lot of legacy peripheral devices, and those devices, in most cases, they really don't offer any security assurance around the firmware that they're running. So they offer no secure boot, and they, in many cases, don't offer any attestation capabilities, meaning that it's really hard for us to get a security assurance about the state of the device that's running in the platforms. And maybe worst of all, they don't really offer a comprehensive recovery strategy, meaning that there is very rarely any out-of-band path to access the firmware storage in case we need to recover firmware or recover the device. And any in-band path to the firmware storage that are essentially firmware update strategies, they usually require the firmware to function in the first place, so that you can get that in-band path over PCIe or other major buses. And the challenge that we also face is that between different vendors of the devices, if they do offer some firmware update, firmware recovery strategies, they're very different. So we end up having a patchwork of different solutions for different devices that's not always want to function correctly. And sometimes one solution that we sometimes see when it comes to firmware recovery is essentially rolling back to some old read-only piece of flash, which usually contains firmware that was created during the device manufacturing, which pretty much always is very old, very buggy, and could actually create potential security issues in a data center, because we will now fall back to some really old firmware that has non-security issues, and that's could actually be one of the ways that potentially malicious attackers could leverage in order to get essentially force the device into that rollback and then compromise the system through that. So that's one solution that's really not very nice. And what ends up happening is that sometimes even at the hyperscaler case, we see that people end up using different hacks in order to get the recovery at scale that's a closed chassis recovery, and that sometimes includes even things like running pretty much spy programmers to every device on the board, or at least every critical device on the board inside the closed chassis, so that you can actually get some form of recovery when things break. And that's really not the state that we would like to be in. And over the last couple of years, as the hyperscalers really grow in their operations, we see there is a push for more robust recovery methods, because unless something really critical happens, we really want to be able to do all of this in a closed chassis methods where we don't need to send any people to the data center to actually fix stuff. We want to be able to fix stuff remotely through our management network. So that's kind of one push that's happening in the industry. At the same time, NIST came up with a set of really good guidelines about firmware recovery that's encompassed in the SP 800-193, and some of the submissions to OCP, like Project Cerberus from Microsoft, introduced this concept of platform root of trust and a component root of trust, which tie really nicely with security solutions that we really want to get throughout the industry. And maybe last, which is very, very critical and maybe even more immediate, is that we see push for or increased focus on device attestation. And there are some proposals that are being worked on through both PCIe SIG as well as DMTF that help us address attestation really at scale using cryptographically secure information that we can retrieve from the devices. Because we really don't want to depend on self-reported information from the device. We want to be able to get something that is cryptographically strong to actually get a security assurance that we need. And we really need to build on this momentum and start thinking about more scalable recovery across the whole data center and all of the devices that we have in the platform. Now, when do we really want to recover? First of all, we want to be able to recover from a bricked state. Flash memory is not impervious to errors. No random bit flips happen, even though they're rare. And whether that's a random event or a malicious occurrence, we want to be able to recover from a scenario where enough firmware, enough critical parts of the firmware is corrupted to a point where the device essentially cannot boot at all. And in such case, it pretty much offers no in-band path for recovering the firmware. And it's, in most cases, it offers no out-of-band path either. And that's kind of the worst case scenario where the device gets bricked. There is really no recovery path to it, and it essentially needs an open chassis intervention, either someone swapping a device or swapping and reflashing the firmware in the device. So that's kind of one place where we really need a robust recovery scenario. Other items are any non-critical corruption. So either that's some bit flips in firmware that's not really causing any major issues, but may cause some stability issues. Similarly, for example, corruption of the configuration of the device. If you're running, let's say, the firmware that you're expecting to run, but the device doesn't really behave the way it should, or it kind of ends up in some strange states sometimes. It's kind of hard to figure out, what to do then, and recovery in those scenarios is similarly important. Now, when we go one step ahead and we actually have devices that do implement secure boot, then even random bit flips in the flash are becoming even more critical, since essentially using secure boot without a robust recovery is nothing else but architectural way to get into permanent denial of service. Since bit flip in a signed piece of code just means that piece of code is now invalid from a secure boot standpoint. And again, something that may not have been critical without secure boot now essentially ends up bricking the device as well, since the secure boot functionality would essentially reject its firmware. And that's where really recovery needs to go hand in hand with secure boot, because implementing one without the other is kind of, on one hand, desirable because we want to have that capability of making sure that we boot firmware that we trust, but on the other hand, can really lead to some unforeseen cases where the device just doesn't work. And then maybe the last point is that we also want to be able to recover from a non-compliant state. So that's any state where device is running, it's up and running some version of firmware, but it's maybe not the firmware that is in compliance with your policies. So either it's old firmware, or it's firmware that has not yet been essentially verified for operation in your data center. And that's also a case where we want to be able to recover. Here we're usually in a better shape because there usually is some in-band path for recovery, but still we want to be able to kind of do this now more comprehensive way. And in many cases, we need to kind of ask ourselves, how do we actually figure out what's the state of the device? Especially for the non-critical firmware or configuration corruption, that's something that you may not be able to see if you're just looking at a firmware version that's self-reported by the device. If configuration or firmware is corrupted in some way that's not really breaking the device will still report you that this is running some version of firmware. And that's not really telling us the actual state of the firmware, whether the firmware is 100% good or no. And that's really where the MCTP kind of stepped in with the SPDM protocol, which offers a common attestation framework, and it does this in a way that you get if implemented correctly on the device, it gives you a cryptographically strong assurance about the state of the device firmware and essentially what the device is running, including both firmware and configuration. And that's kind of a base, that's essentially a fundamental feature that we can now leverage to get both trust and assurance in what's running on the device. And the idea there is that once we actually have devices that use this feature, we can leverage some trusted platform agent to be able to, both during boot as well as periodically while in operation, essentially check the device state and query it out of band without really causing any performance issues, but essentially be able to verify that the whole platform is still in compliance with your system policies that are driven kind of from your management network down to the platform, to this trusted platform agent. And then that trusted platform agent can essentially verify everyone. However, SPDM, while it helps us with the kind of figuring out what's the device state, doesn't really do anything to address recovery and doesn't really do anything to address scenario where the device may not be responsive. So that's where what we're proposing in the security work group is to create something that we call a device root of trust for recovery. And that's really a very small immutable piece of either hardware or firmware, depends on the kind of implementation, that will be used for the sole purpose of recovery and really an out-of-band way of doing recovery. Because we want to be able to address scenario where pretty much all of the mutable code in Flash is corrupted or doesn't even exist. And we want to be able to get essentially an out-of-band channel to that Flash storage in order to send at least a minimal image that will allow us to start performing recovery, maybe to a point where we can get an in-band path that's higher bandwidth and that can essentially complete the recovery faster, or at least complete reprovisioning of the device faster. With such approach, any type of boot failure should essentially automatically trigger this enter into this root recovery mode by this device root of trust for recovery. And with the MCP SPDM evolution, with the encrypted and authenticated protocols that they're coming up in 1.1 and future revisions, we even see a way that we could essentially leverage authenticated messaging from a trusted platform agent to use this device of trust for recovery for performing a both recovery as well as firmware updates in a more uniform way, where essentially we could have a common way of doing things and fixing the device's firmware in the platform in a way that's universal across devices. And that's kind of where we're going to proposing a essentially common recovery framework where we don't want to reinvent the wheel, and definitely we don't want vendors to come up with their own unique ways of doing this, because that kind of comes back to this point in the beginning of my presentation, where having different ways of doing this for different devices is really problematic, because essentially it causes a lot of friction on the side of hyperscalers, where you're running really millions of devices, and you want to be able to manage them and recover them and attest them in a common way. And that's why we propose essentially to build this on top of MCP. Now, MCP is not a perfect protocol. Right now in the platforms that we have today, it mostly runs on top of SMBus, which is horribly slow. But MCP is also really kind of agnostic to what bus it's running on. So if in future MCP, for example, moves from SMBus to USB or some other higher bandwidth out-of-band protocol, all of this should essentially just carry forward. So we can kind of keep the same foundation irrespective of the medium that we're talking to. And we're proposing to build on top of the existing SPDM messaging and essentially deliver outside of the attestation messages that are defined there right now and future messages defined for encryption. We would like to define a new message that's essentially built to support a firmware delivery. Since SPDM and MCP already creates a path for us to discover device capabilities, devices that implement this mode would be able to essentially advertise the recovery capability. And in a case where the device gets into a bad state where let's say most of the firmware of the device cannot operate, this small immutable piece of functionality on the device would essentially kick in a response to the basic MCP messages and advertise only the recovery capability, so that you can essentially get some communication with the device, negotiate the recovery, deliver some minimal firmware payload that you will be able to then perform recovery of the device. And through that process, you can recover both the functionality and eventually you can recover trust into the device. Because if you're already building on top of SPDM, you essentially have the attestation capability as well. So our goal there is to essentially push this recovery decision to the platform. That kind of alleviates some of the burden on the devices, because if we were thinking about, let's say, even like AB versioning of firmware on the device, firmware storage, that kind of carries some challenges for the devices, where the devices now need to have more storage, need to manage it, and so on. This way, you essentially push all of this to the platform and to this trusted platform agent that really provides the recovery images to the device. You can now essentially seed all of the storage requirements to the platform, or even to the management network, where this trusted platform agent maybe doesn't even store those recovery images on the platform, but it fetches it receives those images out of band from the management system. And you really see this functionality of running recovery to this trusted platform agent that is much more capable than some small immutable code in your device. This way, you essentially the only thing you do is you open up a recovery path, and you let this platform agent, whatever it is, whether it's something like a Cerberus or Titan or just a PMC essentially that already talks MCTP protocol, you're essentially now able to seed all of orchestration of this recovery to that device. And since we can achieve trust in the device through comprehensive attestation that's cryptographically strong, you run recovery, you get to a state where the device is functional again, and you can then use the same MCTP SPDM protocol to rerun attestation, check compliance, and recover the trust in your whole platform, in the device, the whole platform, and eventually into the whole data center. And that kind of builds a robust, scalable solution that will work with anything from a small data center to the massive deployments that hyperscalers use, and will really simplify a lot of stuff. So that's kind of our call to action, to essentially leverage the new common security protocols, to really think about device attestation, and build that into all of the server products, because that's really the base for gaining trust in the system. Now, in many cases, you could even think about focusing on attestation first before you focus on secure boot, because if you have cryptographically strong and secure attestation, you can see the kind of the compliance check to the higher level entities like a platform agent or even like your management network, where you can essentially gate access of a server to your network by the attestation results. So if you have cryptographically strong attestation, you can essentially work with that in even when you don't have secure boot, and have full trust in the whole server just through attestation. And we really need a common path for some agent on a platform to recover devices, and with MCTP being widely deployed, and with the SPDM protocol being defined and slowly implemented by vendors, using that as our common path for all devices is probably the best way forward, especially in the short term, where we can leverage that across the server and across the data center. And no, we are a very open community. So if you look for OCP security work group, no, we're a open, quite active group that meets regularly. So if you want to contribute or discuss challenges with recovery or with attestation, we're always more than happy to talk. You will find all of the information at the links that are here. We have a mailing list. We have a wiki where you can find all of the documents that we're working on. They're all public Google Docs. Our link to join our weekly calls and things like that. So no, we won't do any Q&A, unfortunately, because we're not in person. But if you ever hop in on that call and have some questions, or join the mailing list and send questions about this topic, we're more than happy to answer any of those. So thanks for listening, and hopefully see you next year. Hi. Hi. We actually can do a little bit of Q&A. When I was recording that, I wasn't aware that there's going to be a Q&A. So I see there are a couple other questions. Just looking at those from Todd and from Silvio. Todd asked, what's the best method for balancing the trust that comes from immutable code along with ability to patch vulnerabilities, which comes with mutable code? I would say that the primary way is essentially keep the immutable code as small as possible. In some cases, some silicon solutions offer some form of patch infuses or stuff like that for immutable code that kind of gives you kind of late patching capability. But I would say that essentially immutable code just needs to be as small as possible. Sylvia mentioned that the recovery spec is password protected. I don't think it is. I will check, but I don't believe it is. I believe it's public. And Daniel Egorov is asking, do you have a way to make sure that the device root of trust for recovery will not be possible attack point and can be used by an attacker to trigger system reset and install firmware with security issues? So the goal of the device root of trust for recovery is primarily to be kind of a fallback solution when the device cannot boot itself. So in this sense, without corrupting the flash first, you should not really be able to trigger it. But no, of course, like especially since it would be immutable, it would need to be very carefully designed with also using formal verification to make sure that we are not actually building more holes in there. I see a question from Doug about PLD and firmware update over MCTP. I think that's a possible solution. I need to take a look at PLD and firmware updates myself, see how it scales. The idea here was to essentially use MCTP for security-related issues, and I see recovery as one of those. We're also in the group, we're discussing solutions, how to do very minimal base recovery over pure SM bus, and if essentially, especially when we want to have this device of trust for recovery have a very minimal ROM TCB. In some cases, putting MCP stack is not something that is very viable, at least in the short term. So we're looking at possible solutions of providing kind of a bare bones SM bus based recovery that can then bring in an MCP stack and kind of do the rest, kind of more advanced stuff over MCP. So definitely, if you have time, join the call on Tuesday morning, and we can discuss more about that. There's actually, I think next week there is going to be a proposal or this description how the type of bare SM bus type of recovery could be done. And I see that, Sylvie, that it's not password but restricted. I will definitely take a look at the permissions on the document and see if we can open it up more. So yeah, looks like no more questions. I think we have maybe 1 more minute left. So thanks for listening, and hopefully we'll have time to join some of our calls and both help discuss and contribute to the work. Thanks.